Hello everyone, I'm Ayush Mishra, a PhD candidate at the National University of Singapore. And I'll be talking about the Great Internet TCP Congestion Control Census, which was a measurement study done in late 2019 to identify the different congestion control algorithms run by servers on the internet. This work was done in collaboration with my colleagues Shankpang, Atisha, Sameer, Raj, and my advisor, Dr. Ben Leong. The internet is the world's largest distributed system. Every day, billions of users use it to do everything from playing games to managing businesses. And this is largely made possible due to a large number of distributed algorithms. For example, when it comes to sharing network bandwidth, distributed algorithms like congestion control play a key role. It is therefore no surprise that congestion control has lasted for almost as long as the internet has. As the internet has evolved, both in terms of provisioning and the nature of the applications that it supports, so has congestion control. And as a result, we've had a largely heterogeneous mix of congestion control algorithms on the internet, as has been verified by previous studies marked in red on the timeline. Most of these congestion control algorithms have not been specifically designed to work with one another. However, all of them have coexisted on the internet because they all react to one common network stimuli, which is packet loss. In fact, for most of them, packet loss is the only congestion inference mechanism that they use. However, in 2016, Google introduced their own congestion controller called BPR, which used bandwidth estimates in RTT to infer congestion on the network instead of packet losses. It has since been deployed by Google to support services like YouTube and the Google Cloud Platform. Since BPR, we have also seen the introduction of other congestion control algorithms that also explore alternate ways to infer congestion on the network. This essentially marks a paradigm shift in how congestion control is done on the internet. What we now have is essentially different congestion inference mechanisms that work and interact with each other on the internet in ways that we don't completely yet understand. And we care about this change in the internet's congestion control landscape because it can affect network characteristics, provisioning choices, and overall connection level fairness. However, we feel that before looking deeper into this issue, it's a good idea to have a look at what the playing field actually looks like. Therefore, we set out to conduct a congestion control census among the 20,000 most popular websites on the internet. And it turns out this is a non-trivial problem for a number of reasons. For one, we would have to somehow isolate the internet's network dynamics from the congestion control algorithm's behavior. We would also have to decide on extracting a common feature from all our measurements in order to identify all our target congestion control algorithms. Lastly, since we aim to conduct our measurements over HTTP web page downloads to maximize the number of websites that we measure, we would have to be constrained by the size of the web pages that we download. Our solution to these problems was a measurement tool called Gordon. Gordon addresses these issues through a number of design decisions. Most network dynamics, like change in bottleneck bandwidth and packet losses, happen at the connection bottleneck. Gordon therefore attempts to isolate these network dynamics by localizing the bottlenecks, thereby being able to control the connection's characteristics more directly. Gordon uses the congestion window as the common feature to be measured across measurements. It does this because most of our target congestion control algorithms are window-based. The ones that are not have a cap on the maximum number of in-flight packets they are allowed to have, which effectively becomes their congestion window. Now, since the congestion window is the maximum number of unacknowledged packets a remote server is willing to tolerate, Gordon measures the congestion window of a remote server using the following technique. Gordon initiates a connection with the server and drops all the packets that it receives. It does this till an RTO is triggered and it receives a retransmitted packet, which it accepts. During this procedure, it counts the total number of unique packets that it drops, and this becomes the size of the first congestion window. Next, Gordon starts a fresh connection, and this time it accepts all the packets in the first congestion window until it starts dropping packets again till it receives a retransmitted packet. In this scenario, now the total number of unique packets that Gordon would have dropped would equal to the size of the second congestion window. By following this procedure iteratively, Gordon is able to plot out the entire Sieben evolution graph of the remote server. Lastly, Gordon must also be able to identify congestion control algorithms within short HTTP page downloads. It does this by trying to maximize the number of packets it receives by crawling the target websites for the largest web objects it can find. It then uses the smallest MTU size allowed on the current connection path to make the connection and therefore plot out longer Sieben traces. During the measurement, Gordon also emulates a sequence of network stimuli, which it uses to elicit different responses from different congestion control algorithms. Through the course of the connection, Gordon first allows the congestion window to rise and then first emulates a packet drop when the Sieben exceeds 80 packets. After this, it changes the bottleneck bandwidth once it has received 1500 packets from the remote server. Both these network stimuli are emulated while maintaining an RTT of 100 milliseconds. The exact reason for having these exact numbers is discussed in more detail in the paper. Given our final network profile, the optimum web page size that we're looking for is about 165 kilobytes. Here, we have Sieben evolution graphs obtained by a control server running some common congestion control algorithms. As you can see, we can differentiate between most congestion control algorithms based on the shape of the Sieben evolution graphs alone. In case there are two congestion control algorithms that have very similar shapes, Gordon will classify them together. Before we actually get into measuring actual websites on the internet, we wanted to measure the classification accuracy of Gordon. To do this, we set up control servers in various locations around the world and measured it using a local machine. Later on, we switched the configuration with the remote servers measuring a locally available test server. As we can see, our classification accuracy for most of our variants is more than 90%. In some cases, we have classified multiple variants that have similar Sieben evolution graphs together. Our measurements were done between 11th July 2019 and 17th October 2019. We made these measurements from servers in 5 different locations in the world. We did this to be able to detect if different CDNs in different regions were using different congestion control algorithms to serve the same websites. We also found that about 16% of the pages that we were measuring were less than the optimal size of 165 kilobytes. In such cases, all classifications were made on the best effort basis. We also came across around 1,300 unresponsive websites that did not respond to Gordon's rather aggressive measurement methodology. These websites generally had DDoS protection, which prevented us from making multiple connections. Gordon did not classify any website as using 2 different variants in 2 different regions. We therefore found no evidence of CDNs deploying different congestion control algorithms in different regions for the same websites. Therefore, we have consolidated the numbers from all our regions following the rule that if a website has been classified as some variant in one location, then we consider that website to be deploying that variant in all locations. Overall, we can see that Cubic is still the most dominant TCP on the internet based on website share. In second place, we have PBR, which has seen unprecedented adoption even though it was introduced in the Linux kernel in only 2016. We also saw 167 Google-owned websites that were deploying a slightly different version of PBR, which we refer to as PBR G1.1. This newer version of PBR v1 differentiated from the original PBR in the aspect that it was more gentle towards an emulated packet loss. This finding was corroborated by Google. While Cubic is dominant by website share, the distribution by popularity and traffic share paint an entirely different picture. For example, if we consider just the top 250 Alexa websites, then PBR actually has a larger share by website count when compared to Cubic. This share for PBR is further increased when you consider the traffic share of these individual websites. By extrapolating the percentages reported by the Sandvine report, we estimate that more than 40% of the downstream traffic on the internet is controlled by PBR. Our measurements also had a large chunk of websites that remained unclassified due to a variety of reasons. To investigate this further, we ran a variety of custom network profiles on them to infer something about their congestion inference mechanisms. We found that there were a significant number of websites hosted by Akamai that seemed to deploy the same unknown variant. This variant, which we call Akamai CC, did not react to packet loss, and its CVEN closely followed whatever BDP got and emulated. We think that it's likely that this congestion control algorithm is a variant of fast TCP. During this investigation, we also found a number of other websites that were deploying interesting variants. For example, we can see that Amazon.com and Yahoo.co.jp both have deployed congestion control algorithms that have more conservative than usual slow starts. We also found Sihu.com, which did not respond to any of the network stimuli that Gordon emulated. If you look at our results in comparison to the previous measurement studies, we can see that the TCP ecosystem is becoming increasingly heterogeneous. In fact, now we have a new class of rate-based algorithms that are emerging as the new contenders on the internet. The deployment of Akamai CC points towards an even more complex mix of congestion control algorithms being deployed on the internet, which means that we can only expect the internet to become even more heterogeneous in the future. While Gordon has been able to successfully classify websites on the internet, there still remains room for improvement. For example, we still need to investigate the unresponsive websites in order to further increase the size of our dataset, and probably use smarter clustering algorithms to better analyze our unclassified websites. We would also like to experiment with a wider gamut of network stimuli. Finally, we would want to extend Gordon to identify more recently proposed congestion control algorithms like COPA and PCC-Vivace. We think this would be possible by measuring features that would better reflect the sub-RTT behaviors that these algorithms show. We have been experimenting by using sending rate as one such feature, and we have seen some success in identifying COPA and PCC-Vivace in local testbeds. In summary, we measured the Alexa top 20,000 websites on the internet, and we have found that PBR is poised to overtake Cubic as a dominant TCP in the wild. We are witnessing a paradigm shift in how internet traffic behaves given the rise of rate-based algorithms. This essentially represents a fundamental departure from how congestion control has traditionally been done on the internet. Thank you for your attention, and I look forward to your questions and comments. You can email me your questions and comments on my email as shown on the slide. You can also gain access to Gordon on GitHub.